Here I will construct a simple circuit. First, we have to look at the circuit diagram. We start from the output of the DC supply. This is the positive, so we construct this circuit from the positive of the DC supply. So I use a long cable so to make this one more flexible. Now, if you look at the circuit diagram and imagine the current, once we turn this one on, the current coming from the positive side all through here, and then this is our RA, or in your circuit diagram you will see R1. Now this is plug here. I connect this one here. Now the current here, this is the conductor here, will go through here and passes through the resistor, coming back here. Now remember here, if you can have a look, there's a no connection. So the current doesn't go from here to here. It goes from here to here. And you can use any color you like, but maybe I use red here still. And if you follow the circuit, it will pass through a switch. So this is the switch here, and this is the symbol of the switch. Connect this one here. Again, there's a no connection here. So, and also you will see the switch here is open. So in order to close the switch, we have to press this one. So we have the physical connection here. Here I can use a black cable. So we turn this one to the negative side of the power supply. Now let's see what happened. When I turn on the power supply, the current will flow from the positive here, through the cable or the lead, through the resistor, and then through the switch. Now it depends, of course, whether the switch is in physical contact or not. And it will pass through and return to the negative side. So if everything connected, this will be a complete circuit. Now let's turn on the DC power supply. And you can see the output here is 4.99 volt, is close enough of our set voltage, which is 5 volt. Now there will be no current flow because the switch is open. So in order to have the current flow, we have to turn it off. Now you can check it. The main display here is volt. However, we can turn this one to ampere. So it will display the current. And you can see here, there's a no current output. Now, if we turn this one on or press this one, you can see here is 0.026 or 27 ampere. And there is a current flow from the DC power supply through the circuit here. And now if I release it, there's a no current. Now sometimes I find when we later measure the voltage or current, this here, it's because the contact, it will affect the value. So I will tend to, in this laboratory, to remove the physical switch, and we use the switch from the power source as our switch. So I can reconnect this one here. And you can see here, if I turn this one on, it will give you 0.027 amp, and 4.99 volts. Now I want to measure the voltage across the resistor. Now the key word here, I say again, is across. So what it means is when you measure the voltage, you're putting between the 2 points of your electrical component or your resistor. I will put this one here. The reason is this is voltage, and I will use common here. Okay. Now I'm going to put here. When we measure voltage, we have to this time think about which side of the resistor has higher potential difference or higher voltage. Now the reason there's a power or there's a current flow is because there's a voltage. Voltage just like a sort of pressure push the current from here through the circuit, and during this one it will lose the energy. So this side here is all high voltage. Now of course we have to assume there's no energy loss within this part of the wire cable. So what we can say is this side here is high voltage and this side here is low voltage. Now when we use the multimeter here, we always put the low voltage at the common, because common is like a reference point. It assumes this is the zero. So what I mean is if we put here, we'll expect with respect to this point, it's going to measure the voltage at this point. And we know this is low or zero, in fact, and this should be 5 volts. Let's see. Now, another thing is I'm measuring the voltage across, so I don't need to do anything about the circuit. I just plug the voltmeter across, and I turn the digital multimeter into voltmeter. And what range I use? I expect the voltage is about 5 volts, or put it this way, the maximum voltage in this whole circuit will be 5 because the output here is 5. So I will push this one here. No, it's too sensitive. 2, it means the maximum range is 2. It's also too sensitive. 20 is a good choice. Let's see. Don't worry about this negative here. It's just a little bit stray voltage, very, very little. And now I turn on the power supply. And you can see here, this is 5 volts, and you can see this is positive 5. The meaning is common is the reference. So it will say, assume this is 0. The red is 5 volts more than this one. So yes, this is what we expect. And you will see if I turn the selector from 20 to 2, it's .OL, it means the range is not right. So we can turn it up. Okay, now how about if I turn it into 200 here? You will still get 5.0, but you lose information because you only get 1 decimal place displayed. So I will prefer this one, and this is more sensitive, 5.00. So in a way, you have 3 significant figures. All those slightly difference, 4.99 or 5.00 is good enough. Next, think about if we reverse the polarity. It means if somehow we change this one and put this one to the positive, and this one is, see what happens. Now it's a negative 4.99. It sort of makes sense because I say the digital multimeter will think the common as the reference point, it means reference 0, and measure the voltage with respect here So it measures the voltage at here with respect to this one. Now, in reality, this is 5 and this is 0. But now we force this one to 0, the reference point. So this one is 5 volt lower than the reference. It means from this point, 5, 0. If this is become 0, this is become -5. The difference is still 5. It depends on how you choose the reference point. So from here, it means this is 5 volt lower than this one. This is what it means. And if you put this one, switch it back, remember the common is the reference. This position is 5 volt higher than this one. So it makes sense because this is what actually it is. Next, I want to measure the current passing through the circuit. Now, when you measure the current passing through the circuit, it is more challenging because you have to decide which point you are going to measure. So for example, if you look at the circuit, if you want to measure at the point which is the current before it enters the resistor, what I mean is if I turn this one on, remember current, you can use water analogy. So once I turn it on, the pressure will push the water through the water pipe and going to here. And this, of course, if you use water analogy, will push it through the resistor and coming back out here and return to the power supply. During the water passing through here, the water loses its potential energy. Okay. Of course, water won't lose potential energy, but you can still imagine just like a waterfall. It still sort of makes sense. Next, if we want to measure the current before it enters passing through the resistor, so it means we can measure the current any point here before it sort of enter or passing through the resistor here. So once we identify which point is before, we say is this point. So any point is okay, any point is okay. But I use this one because I can unplug it. So the idea is find the point on the circuit, identify this point in the wheel circuit here. So in the wheel construction, your circuit, it is this point before it enters the resistor. And what next? This is important. If you think about we are going to measure current, we have to plug the current or the water into our meter. So it means if you want to measure current, you have to disconnect your circuit. Now, with the water analogy, we are saying is the water wheel coming through here, but once it's disconnected from your device, this water, our analogy, will come out from this point. Now, how to measure the flow of the water? We plug this one into the meter. If we want to use this multimeter, measure the current, we have to choose which plug we are going to use. Now, we know in our lab, we're going to measure a low current. So we can use this one. It means the MA range or any current lower than 200 milliamp, we use this one. If any current higher than 200 milliamp, we use this one. So this is a safer one. For example, if you try to measure an unknown current in some practical cases, and you are safer to use this one. However, in our lab, we know this won't be the case. We know the current is already, because the design of our lab lower than 200 milliamp, so we can definitely use this one. Now, think about if we use water analogy, the water coming through here, coming out here, so we put the water into the current meter, or this is how we measure it. Now, but where the water comes through inside, you must let the water coming back out. Yep, the water will come back out from the meter. Here, the common mean common for any type of measurement. So I use another water pipe, collect the water. But where it should go, if you think about it, this is what it should be. It passing through, but now we just like cut this off, disconnect this one, intercept the water, plug this one through, the water come back out, so you must put this one back to the point you disconnected. Now we can see this one technically we are saying is we connect the current meter as in series of this one. Why in series? Current flow here, or the water flow through this one, back here and to here. So this is in series. Now, which one we should use? Remember, we are measuring current, so we are going to use either here or here. However, this is a DC current, so we expect we use this part. And we are going to measure MA, so I will choose this one here. Again, this number here is just because the stray current or the sort of still offset, whatever here, don't need to worry. We haven't turned on the power supply yet. Now I'm going to turn it on. And you can see here the reading. The reading is 27.5 milliamp. If you check the calculation with the nominal value of 5 volt and 118 ohm, you will find it's 27.8 milliamp. But remember, the resistor here is not really exactly 180 ohm. It's slightly off. So again, that's why this is slightly different from what you expect. After you finish the measurement of current, the most important thing is turn it off. Turn off. Now, this is important because it's a good habit to put everything back to the default. And put this one back to here. So this is our default circuit. Next, we're going to measure the current after it passes through the resistor. So it means technically we can measure the current at here all the way to this point. And I will use this one because I can unplug it. Now, think about the water analogy. Water coming out from here through the cable or water pipe, through here, and then passes through the resistor to here. Now think about if I want to measure the current at this point, I need to, same argument. I have to disconnect this one. Now the water, of course, once you disconnect, the water will coming from this point. So I have to receive the water. The water is coming from here, or the electric current. So I receive the water or the current. The water will come from here. Now I can plug this one into the meter. Remember, we use this one for current measurement. This go into the meter, come back out from the common. So I receive this one back here. Again, now I'm connected this current meter in series with our resistor. What I mean is the current flow through here passes through the resistor, coming back out here. Now we interrupt this one. Instead of go straight back to the DC supply, we interrupt it. We connect the current through and push it through into the meter. It coming back out from the common, and now we connect back to the DC supply. Next, we want to know how we choose. Remember, this is the digital multimeter, multifunction. We have to turn this one into a current meter. It means it measures current. Turn this one here. The range we use is MA again. This is just the offset or straight. Now I turn this one on. And we can look at here, 27 milliamp, or we check here, 4.99 volt. And here, 27.5 milliamp, exactly the same number we measure when we measure before the current passing through here. So what we know is now makes sense because there's no branch. So all the current or the water through here along the circuit should have the same flow. It means each second should have the same charge of flow through the circuit if there's no branches. And this is the case. So the current, if you measure at this point, any point in a single loop circuit, it will be exactly the same. Now turn this one back to default. Remember, this is the good habit.